Okay, so the next type of energy we're going to talk about is potential energy. And remember, for potential, we always use the letter U. We're going to talk about UG for gravitational potential and US for elastic potential. And this is always stored energy, so energy that has the potential of becoming something else. So the two ones that we're going to focus on, it's stored energy that can be readily converted to other forms of energy, such as kinetic or thermal. And forces, there's only really a couple, two big forces that can actually create this useful energy, and that's they're conservative forces that are gravity and elastic forces. So those two forces always exert, or like with elastic, always want to be at homeostasis, so then they could store that energy ready for a later use. And then, of course, we have the opposite, which are forces that, like friction, that can't store useful energy, because once something's friction, it's useless to us. We call those non-conservative forces. So energy is just lost to the environment. But looking at our two different types of potential, we're going to look at gravitational potential, which is energy associated with having some height above the ground, and elastic potential energy, which is stored energy in a spring. So we have a formula for gravitational potential and a formula for elastic potential. So gravitational potential energy, if I think about lifting something up, I am overcoming the force of gravity. So if I think about before work equals force times distance, well, the force I'm overcoming is gravity, which is mass times gravity, and the distance that I'm traveling is the height, or whatever I change in the y direction. So gravitational potential energy is proportional to the change in its height, and if we put the ground or the earth as being our 0 point, then the height above that is going to be our final y position, and that'll be how much potential energy we have. And all it depends on is the height. And if I look, I got this little picture over here. There's two different paths up the hill. There's path B, which is very exponential, very difficult path to travel, and there's path A, a little bit more lenient. And in both cases, though, they start at this height and they end at this height, so they have the same change in gravitational potential energy. All right, so in this case, for example, both objects start at the same height. So block A gets launched at an angle. So it goes down, it launches up, and then it falls down to the ground like a regular projectile. Block H just launches horizontal, so it just goes down to the ground. So when you use conservation of energy, which we'll talk about more, both the objects start at the same height, and so they have the same potential energy. Since they end at the same height, which is just the ground, they have the same kinetic energy, even though they took different paths. So therefore, they'll both hit the ground with the exact same speed, just at different angles. The horizontal one will have more velocity in the horizontal direction, and the angle one will have more velocity in the y direction, but their overall net speed, which is the vector sum of the two, will stay the same. So I got a quick check. Both marbles, they start from the same height. And my question is, which one will be moving faster at the bottom? And of course, like we just talked about, they will have the same speed at the bottom. All right, so we got another quick check. Now we're going down some different slides. And again, this is the same concept. If we all start at the same height, although we all go through different paths, when we hit the ground, we will all be traveling at the same speed. So it's independent of the path that you take. Okay, so the other type of stored energy is elastic potential energy. Now, and what we'll typically look at that is a spring, and we'll do a lab, this unit, to help us out with that. So the Hooke's Law lab will get us a little bit more into springs. That is actually lab 3.4, because I've added another lab. But anyway, a spring always starts at equilibrium. And as I start to push it in, I exert a force onto the spring. And the more and more I push it, the more force I have to push with, and the more energy that gets stored. So our formula for this is US is 1/2 K delta X, or X squared. Delta X refers to the distance that you stretch it, and K, and this is what we'll do in lab, K refers to the spring constant. It's how stiff or rigid the spring is, and that's measured in newtons per meter. And then that'll help us determine how much energy is stored. All right, another quick check. Hockey puck sliding on smooth ice has no friction. At 4 meters per second, comes to 1 meter high hill. Can it make it to the top? Well, that means it has kinetic energy, and at this point, it needs to have potential energy. The question is, before we had to figure out, well, what's the acceleration on the hill? And then as I go up the hill, it slows down. Would I still have velocity at the top? Now it's actually really easy. I can say, well, my kinetic energy is 1/2 mv squared. So that's 1/2 the mass. Oh, I don't know the mass. That is going to be equal, though, to the gravitational potential energy at the end, which is going to be mgh. Oh, okay, so my masses cancel. Great. So the height that it can make it to is going to be, I'm going to move that g over, so it's going to be v squared over 2g. The height that it can make it to, the brand new formula, it's just derived from this. So it's 4 meters per second. That quantity is squared over 2 times 10 meters per second squared. So I got 16 over 10. 16 over 20. And I do know that even without a calculator, I know that 16 over 20 is going to be less than 1. So therefore, I can say that the puck does not make it over the hill because it didn't have enough kinetic energy to start to have that amount of potential energy to end. All right, here's a partner problem. So this will be a problem that we'll look at during class. And we have an archer pulling back a bow on a string. So this is an example of elastic potential energy. So elastic potential energy, otherwise known as us, is 1/2 k delta x squared. Ooh, that gets a little different then, because I have a few different variables. I have a force and I have a distance. Oh, but any work being done on it is also equal to force times distance. So we're going to have to take a look at this one and make sure we understand the variables and when we can use them. And we'll take a look at that during class. We do have one more type of energy to look at, and that's going to be thermal energy, and we'll do that in the next segment.